So the extension of our basic idea that we looked at yesterday of growth and decay, we're going to take into account some external conditions. So the classic example is the cooling down of something, or the heating up. You know, what do they call it? The Newton's cooling. Anyway, there's some name. And so the basic idea with this is we know the temperature of an object will never be lower than the temperature of its surroundings if we just leave it to itself. Obviously, if we apply heat to it, it'll heat up. Or if we apply cool to it, it'll cool down. But if we leave it by itself, it could never drop below or rise above the temperature of its outside surroundings. So we need to change the equation slightly. So instead of just being a constant times the population, we now say it's a constant times the population minus n. So some other constant which takes into account the external condition. Similar to yesterday, it is okay to jump straight to the solution. Now, the solution to this particular differential equation, which would be found in a similar way I did yesterday's one, by basically integrating, turning it upside down and going through all that. Well, there's a trivial solution that we don't worry about. If p was simply equal to n, then it would work. Because if p was equal to n being a constant, when you differentiate it, you would get 0. And clearly, if you made p equal n there, the derivative would be 0. That's not the case we're interested in. The solution we're interested in is this one. P equals n plus ae to the kt. So there it is. That's our basic model, but plus taking into some external condition into account. And so if you think about this graphically, we've got our basic exponential curve. Instead of going asymptotic to 0 now, it'll go asymptotic to whatever that external condition is. So we've lifted the whole graph up n, if you like. P still stands for population. Now the initial population will now be n plus a. K is still the growth constant, or decay if it's going down, and T is still time. Well, gee, that is quite an old question now, isn't it? 1993, but anyway. So T was the temperature inside a room at time little t. Capital A is the constant air temperature. Newton's law of cooling, that's what I was thinking of before, Newton's law of cooling, states that the rate of change of the temperature will be proportional to T minus A. Show that. So again, similar to what we saw with yesterday's example, we don't actually have to go and do the calculus. We simply usually are asked to show that this solution works. It fits our model. Okay, well, if T is equal to A plus CE to the KT, if I was to differentiate that with respect to T, so the T, so that's big T, the T, that's little t, okay, so the T is equal to KCE to the KT. Okay. But I know if I rearrange my solution, T minus A is equal to CE to the KT. So I could substitute that in, and I get that the T is equal to some constant times T minus A. So in other words, it's directly proportional to T minus A, and that's what we're trying to prove. So it satisfies the conditions that we've been asked. Okay, now they give us some actual values. The outside air temperature is 5 degrees Celsius. Ooh, that's pretty cold, isn't it? Oh, heating system breaks down, causes the inside room temperature to drop from 20 to 17 in half an hour. After how many hours will it be 10 degrees? 10 degrees. So a few things we need to find. Okay, I now know that T is equal to 5 plus CE to the KT. Remember I said that additional part is that external condition. If the outside air temperature is 5 degrees, what we're saying, we can never drop below it. So that becomes the horizontal asymptote, if you like. We can never go past that. So that's why it becomes 5 plus CE to the KT. We were told that the initial temperature is 20, so therefore C must be 15. Because remember we said that plus C, 5 plus C, would equal the 20. Or if we don't remember that, we could simply substitute in T equals 0, and we get T equals 5 plus C, or 20 in this case. Either way, C becomes 15. So there's our new formula, T equals 5 plus 15e to the KT. Need to work out what that constant is now. So they've given us another condition in there. We know that after half an hour, so T is 0.5, temperatures drop to 17. So we sub that in, and once again we have an exponential equation to solve. So eventually, there we go, e to the 0.5k, undo that, we log both sides. K is equal to 2 log 12 on 15. I mean, I suppose you could simplify the 12 on 15 down, but it doesn't really matter. We're going to sub it into the log anyway. Okay, well, I'm going to leave it as K in the formula because it's too messy to write out that whole thing. But remember, we've got that value stored in our calculator to use. We now want to know when is the temperature going to drop to 10. So when is 10 equal to 5 plus 15e to the KT? So again, another exponential equation to solve. This time we're trying to find T. So we end up with 1 on K, the log of a third, K being that number we just worked out in the last step. Substituting in, I get 2.46167. So after about 2.5 hours, the temperatures drop to 10 degrees Celsius. So basically the same idea, but we've just extended a bit now to take into account the external conditions.